Hey everyone, welcome back to Rocks for Jocks. My name is Alex and I'll be your host for the show. Today I'm speaking with Professor Roger Fu, who works in the Earth and Planetary Sciences department at Harvard. I typically try not to play favorites with any of my guests, but this has got to be one of my favorite episodes so far. We cover a ton of different topics, including planet formation in our early solar system, climate change, science funding, historical earthquakes, and how different cultures study space. So many of my favorite topics jam-packed into one episode, so it's going to be a really good one. If you like the show, please subscribe and send it to a friend. If you haven't seen one of your friends in a while, this podcast could be a great conversation starter to reconnect with them. Or alternatively, if you see all your friends every day, you probably know everything going on in their lives already and are looking for new stuff to talk about. So this podcast could be a great conversation starter with them as well. After you subscribe and send the show to a friend, kick back and enjoy the rest of the episode. Thanks again for listening. Roger, thanks again for meeting with me. One thing I like to do at the beginning of these is give guests maybe 30 seconds or so to introduce themselves and maybe a little bit about who you are and what your background is.
Yeah, sure. I'm Roger Fu. I'm currently a professor of Earth and Planetary Sciences at Harvard University. I study a mix of space rocks and very old Earth rocks.
Yeah, and what was your background like? I think I saw you did your PhD, was it at MIT?
That's right, yeah. Yeah, so I was actually a Harvard undergrad, so I guess you can say I've been at Harvard for 20 years in some form. And then I did a PhD at MIT and then went on to Columbia for a postdoc and then came back to Harvard. In the middle, I did a stint in anthropology between undergraduate and graduate school.
Oh, really? What was that like?
Yeah. That was great. That was very formative. I was in Chile. I was living with the Mapuche people down south. I was studying their astronomy, so it was still related in some way to my science research. But living in a small village and asking people what they believe about the stars, how they name stars, how they use stars to keep track of time and so forth.
Hmm.
So a lot of goat herding and cow herding.
No, tell me all about that. How did you get into it?
Yeah, I think when I was a kid, I must have been around probably 10, 11 years old. I saw a PBS documentary about tsunamis caused by earthquakes in the Pacific Northwest being recorded in oral traditions, right, in the Native American groups up there. I don't know, somehow that just always stuck with me, even though I didn't study anthropology as a university student.
Mhm.
And the idea that legends have a scientific basis, right, and they're kind of another way of seeing sort of scientific observations that we make today in our worldview. Yeah, that's just really fascinating to me. So I was lucky enough to get this travel fellowship after graduation to go and just live with some Native Americans in Chile. And I originally wanted to study earthquake lore, but I found that there was a lot more material for astronomy, and it hasn't been documented, at least in wider publications. So I just did that. So day to day, it was basically just doing what they do as the villagers in the village. So day to day, I basically cut grass, herded horses and sheep around, just whatever housework and farm work there was to be doing. I was 23 at the time, I guess, and you know backbreaking labor seemed really fun. So that was day to day, but at night when we're looking at the stars, every now and then you get these really interesting stories. For example, probably the most important thing that I documented was probably the tradition of naming stars in Mapuche is very different than in the West. They name some stars based on their rise times and their set times, right? So depending on the time of the year, the same name, right, the same star, would be assigned to different objects, right? In our view, they would be different stars with different positions in the sky. But for them, because it rose at a certain time, it had the same significance to them. And it's not because they didn't notice, right, that the stars changed throughout the course of the years. That for them, it was more important that the star rose at a certain time of the night, and that had a certain sort of spiritual significance. So just a very different way of thinking about, what is what in the heavens. And it took me a long time to sort of figure it out while I was there. Of course, it's obvious to them, right? But it was kind of humbling experience and very interesting.
That's great. Yeah, that was maybe the part of your resume that stuck out the most when I took a look at it. Just very unique experience.
Yeah, it's a little random. I have all these publications and then like one publication in Spanish in like this kind of pre-Columbian art journal, right? Anyway, it looked like it was a different Roger Fu who wrote it, but yeah, that was me.
No, that's great. Did you learn their language as well?
Well, I learned as much as I could, I guess. I wouldn't say I was ever fluent, but I could get around. Yeah, and it's just a gesture of respect, I guess. If anyone listening is planning to do field ethnography in a small village somewhere, just learning enough to show that you're really trying is just really important.
Yeah, and I think my background is a little bit in earthquakes. When it comes to earthquake history and tectonic history, there's a lot that I'd say is relied on kind of that oral history, that oral tradition of looking back at what other people experienced hundreds of years ago and trying to fit that into current scientific consensus. So yeah, I guess I have some appreciation for the for going straight to the source and seeing what people experience themselves. Yeah,
Hmm.
it's just a very different way, I guess, of thinking about science than what we normally do today, which is collecting anonymous data and looking at things that way.
Yeah. I did try at the beginning of the trip to gather stories about earthquakes, right? Chile has a very long history with earthquakes, of course. I met a guy who was swept out to sea in the tsunami at the 1960 Valdivia earthquake. Hung out on a log for a few hours, washed back. Anyway, yeah. So stories like that, I think I think that's how people remember it, right? It's not like
Mm.
the magnitude. No one knows what magnitude it was. It doesn't really mean anything. But it's these kind of personal stories, right?
Yeah, that's fantastic. How was that paper received by the journals that you sent it to when you first put together the article about living down there?
Oh, well, let me put it this way. It was the only paper I've ever written that was rejected in two different places.
Oh no.
Yeah, no, I think well, I don't know. I'm an outsider to the anthropology community, of course. So maybe there's a certain culture, a certain way of writing. Maybe I didn't have that, but it eventually got published. It's fine. And to me, it's not the motivation is really just to write it down and have it somewhere accessible because it is true in the for anthropology ethnography community. It is true that like these traditions are getting harder and harder to keep, right? If most young people leave the village, that's true of the village I lived in, just like everywhere else. So just having it written down somewhere, I think was the value in itself, and it doesn't really matter how many people cite it.
Mhm.
I'm just happy it's written down and people will be able to read it many years down the road and know about some of these traditions that hopefully will still be alive and well somewhere in Chile, but you never know.
And then how did that tie into, or I guess how was it transition to a more structured way of thinking about astronomy and astrophysics in graduate school?
Well, I guess my worry at the time was that by the time I come back, I would have forgotten all how to do math and physics. But it turned out actually it was much easier than I anticipated to just kind of pick things back up. So, yeah, I guess if any college students are out there listening, or even high school students, taking some time off, taking a gap year, or a year and a half in my case, I think it was wonderful. It really didn't cost me anything other than that time, which was very well spent. It didn't cost me any sort of delay in my quote unquote career afterwards. And if anything, actually, it probably made me more motivated to go back to graduate school. I think probably that's the most kind of far-reaching consequence for myself. I think it made me realize how important understanding the universe and the earth is for everybody, right? So I was in a village where it was people some people were kind of malnourished, right? And there's a lot of poverty, a lot of alcoholism, a lot of kind of real world problems. And something you hear about all the time is that why are we spending money doing science, sending space probes into the universe if there's still people with basic needs unmet? And when I was there and talking to people, no one there ever asked me that. No one asked me like, why are you asking about these astronomy things, right? Why aren't you trying to do this or that instead? Everybody was just really interested. And when I talked about, the Western, maybe more scientific view of astronomy as well, they were really interested in talking about their beliefs and how they thought the Earth and the universe formed and what it's made out of. So that made me really motivated to go back to graduate school and realize that doing science and asking these sort of existential questions, right, about where we come from, what the universe is, there's value in that. I'm not saying we should spend all our resources doing that, right? But it is important to people and it's worth
Yeah.
doing.
Yeah. Okay. So that leads into something really nicely I'm curious to ask you about is kind of how do you think about that trade-off between putting funding into things like exploring the universe versus putting funding into basic needs and infrastructure and things like that.
Yeah, well, I don't have a number, I guess. That's above my pay grade, I guess, to say how much money we should spend here and there. But I would say if you look at the big picture, we spend a very small amount of money on science in terms of research. The NASA budget, right, overall, it's last time I checked, it's something like 0.5% of the federal budget, and out of
Hmm.
that, actually, only about 10% of that is planetary science research, right? So all of the stuff you hear about, like, you know, latest evidence of water on Mars, potential biosignatures on Mars, potential habitats for microbes under the ice on Jupiter's satellites, potential habitable environment early Venus, all of that research, right, fits into 1/10 of the NASA budget, right, which is itself less than 1% of the federal budget. So it's I would say that level is appropriate, right? Given the sort of interest in these topics, given the well, let's be honest, the prestige I think it brings to our country and to our government, to NASA. I think that's worth it. I mean, if we're up to me, I think it's worth more, but I think at least what it is right now is good.
Yeah, no, that's great. Thank you. Yeah, I guess can you tell me a little bit about some of the details of what you studied in astrophysics?
Yeah, on the more astronomy side of my research, I work on the formation of planetary systems, right? So how did our solar system, right, which has the sun, eight big planets, a bunch of little guys running around, how did this form out of basically a giant ball of almost entirely gas, a little bit of dust mixed in there, 4.5 billion years ago? It's quite a complicated process. We really don't understand some basic aspects of it. So one of the most mysterious parts of this is, well, how do you get dust to stick together? So the biggest piece of dust in interstellar space, i.e., the gas in a dust cloud that formed the solar system initially, is 1/100th or 1% of the size of a human hair, so sub micrometer. Planets, of course, are thousands of miles across. So how did you get the untold number of these tiny little particles to stick together? If you're used to, cleaning your room every now and then, you might see kind of these dust agglomerates, right? Hopefully they're
Hmm.
not too big, but you'll notice that they don't get that big either, right? They don't get to the size of a planet. Like the dust in your
Sure.
house doesn't all come together and just stick into one giant ball.
Mm.
So there's some forces that must be gathering dust and making it stick together over the course of the very early solar system. And these forces are being much better understood now than maybe 10, even 15 years ago when I kind of started in my career. But there's still a lot left to understand. So what I do more specifically is try to understand what are the forces that create gas vortices. So you imagine this protoplanetary disk made mostly out of gas that eventually formed into our solar system. So what kind of shepherded the dust particles in that gas into these vortices and sort of concentrated them? And
Hmm.
my work most directly uses meteorites. So we look at meteorites that actually are pieces of rock that survive from this very remote early time in solar system history and try to understand what are the conditions of that gas, what are the magnetic fields that actually control the motion of that gas, and whether that is sufficient to form planets from these tiny dust particles.
Cool. That's fantastic. And how do you get data for looking at these meteorites?
Yeah, so I'm a lab guy at heart, I guess. I do some field work and some computational stuff, but mostly I'm a lab guy.
Mhm.
So we take meteorites, which are usually pretty precious, right? So you only get a very small amount. You go to museums, you ask them very nicely, you write a little sort of proposal on why it's important to do what you're doing. And hopefully they give you a small piece, usually like a gram or half of a gram. If you try to visualize it, it's, I don't know, size of your pinky nail or something like that. And then you try to, in the lab, at least what I do, is I take this meteorite and I measure it in what's called a magnetometer or a couple of different magnetometers. They basically measure the magnetism of the rock, of that meteorite. Because meteorites, like any other rock on Earth, also, they contain iron, they contain certain minerals with iron that are more or less like little compass needles. They actually align themselves to the background magnetic field when the rock formed. So by measuring the rocks in our magnetometers today, we can actually back out information about magnetic fields that existed when the rock formed a very long time ago. In the case of these meteorites, they're very old. They're about as old as the solar system itself, so about 4.5 billion years old. And we can use that information to reconstruct the properties of magnetic fields in the protoplanetary disk as the solar system was forming. And from that, we can back out, oh, are these magnetic fields enough to concentrate dust particles? Are they responsible for the formation of planets and leading us to have the solar system we have today?
Wow. Okay, cool. Okay, so to recap for the listeners, you take these meteorites that have fallen to Earth from, which were originally formed in other solar systems or other parts of the universe. You examine them for basically how their magnetic field was looking when the meteorite formed, and then use that information to learn about how magnetic fields work in general and how they form either planets or larger chunks of rock in different solar systems. Is that right?
Yeah, that's right. But the one thing I would change is I wish I could get meteorites from other solar systems, but everything is from our own solar system. So just very early on
Okay,
in our solar system.
cool.
There have been literally a couple of little rock particles that have been harvested in our solar system that came from interstellar space. But the vast, vast, vast majority of meteorites are from our own early solar system.
Fantastic. When we look at meteorites on Earth that have originally formed in our early solar system, do you mean all the way back at the beginning, or how old are most of the meteorites that you look at, you think?
Yeah, that's right. Most meteorites are very old. They're about the age of the solar system, a little younger, so around 4.5 billion years ago. Yet, though the reason we use meteorites, right, is because the Earth, for example, and other planets have all these surface processes that if you want to study the very oldest rocks is actually kind of detrimental, right? So the Earth, most of the Earth's surface is less than 200 million years old, right? Which sounds old, but it's only about 5% of the history of the solar system. And that's because the Earth has plate tectonics and it recycles its crust very efficiently. The oldest rocks on Earth are only about 4 billion years old, which again sounds very old. It is very old, but it's still
Yeah.
half a billion years younger than the age of the solar system, right? So to understand what happened in that very early few million years, when most of the planet formation actually occurred, we have to look elsewhere. And it turns out meteorites are the perfect place. So basically, they formed in the protoplanetary disk in the first couple million years of the solar system. And then they were basically stored in cryogenic conditions in these asteroids, right, or in the asteroid belt and elsewhere. And so it's kind of a lucky scenario for us. It's basically the universe has provided this deep freezer out in the solar system that has preserved these rocks relatively well. into the present day. And so we take advantage of that and kind of look directly into the early solar system by looking at these meteorites.
That's so cool. I had a professor in college who was obsessed with the age of rocks, learning about the oldest rocks that we could find on Earth. And all of his science pop culture that he told us about was related to the drama between different scientists to see who could find the oldest rocks and which areas had certain chemicals that indicated different ages and which machines were best for measuring the relative amounts of elements in these rocks for determining how old they were and that kind of thing. Sadly, I forget a lot of it several years later, but I remember that being really exciting drama at the time to learn about. And then do you also do any work with paleoclimate? So learning about climate in Earth's history long ago, or a climate of other planets from billions of years ago, or anything like that?
Yeah, I do some work on paleoclimate. The paleo in that case is much younger than the paleo in the early solar system or my other work. Yeah, we've been trying to use cave deposits, right? So stalagmites, right? So these kind of spike-looking things that grow from the bottom of the floors of caves. Using these and trying to reconstruct the flooding history of a region. So it's probably most useful as a way to understand natural disaster hazards, right? So if you have, for example, instrumental records, so by that I mean a weather station or rain gauges back, let's say 150 years, 200 years, maybe at most in a certain region. That doesn't necessarily tell you what kinds of floods that region is really capable of, right? Because you could have a once in a 500-year flood, once in a 1,000-year flood that, although unlikely to happen any given year, when it does happen is a big deal. Let's just say. So using these records and understanding what kinds of floods happened in a deeper past, so let's say a few hundred, a few thousand years ago, is important for us to understand the the consequences of our choices today in terms of where we build, how we change the landscape, and of course more broadly how we change the climate, right? Because that those deeper records tell us a more whole picture, a fuller picture of how floods and these extreme rainfall events can happen in a certain time, in a certain place.
Yeah, absolutely. And I'm assuming this is field work that you go out and collect, or you have maybe some partners that you work with that go out and collect it. How does that process work for you?
Yeah, we do a mix of field work in caves as well as to other places. For these projects, we've been mostly going to Brazil, partly just because there's some caves there that are well studied in other ways, so we have some kind of good context for these caves. It's a lot of fun. I'm not a caver. I had never done that before I got this job. But since then, I bought a helmet. I got a suit, and it's been really cool to go in these caves and kind of go beyond where the cave is kind of open for tourism, right? And to kind of go through these really narrow passageways and things like that. So it's a lot of fun. One of the things that kind of brought me into earth sciences originally, when I was a college student trying to decide what to do with my life, was field work. I thought, oh, if you can get paid to like go to nature and walk around and look at stuff, that sounds pretty cool. I always liked hiking, and now I get to do, at least for a small part of the year, right? Sort of
Yeah,
hike for
yeah.
work. Yeah, so that's part of field work we do. We also do a lot of field work in very old rocks on Earth. So we've been to Australia a bunch of times, probably trying to go again later this year. And we have been collecting rocks to understand the motion of plates. So understanding plate tectonics on Earth as it functioned on the very early Earth.
That's great. So, how do you tell me a little bit about your trips to Australia? What kind of rocks have you gotten down there, and what have they taught you about plate tectonic motion?
Yeah, well, our trips to Australia, we've gone quite a few times at this point, and every time it tells us something a little bit different. But overall, if I were to summarize the story as succinctly as possible, I would say that it's surprising from the evidence how similar the early Earth was to today. What I mean by that is that the forces that control the Earth's surface today on long time scales, right? much of it revolves around this idea of plate tectonics. So the Earth's surface, unlike any other planet we know of right now, is divided into these large plates, right? These are kind of more or less rigid pieces of crust that collide with each other. Sometimes one goes under the other, sometimes more gets formed. Famously, of course, the San Andreas Fault is the boundary between the Pacific Plate and the North American Plate. And they kind of move relative to each other at these very slow speeds, centimeters per year, but over time they accumulate. And that's why we have the Atlantic Ocean, for example, which opened up, about 200 million years ago. So this sort of motion, right? These plate motions on Earth, they might seem kind of abstract. Like I don't feel my plate moving, right? Because it's going really slowly. But it really has very, very important consequences for the Earth's surface. So for one, it regulates temperature on very long time scales. So I'm not talking about glacial cycles or climate change. I'm talking about millions, hundreds of millions of years. Over that time, it's believed that the main control in the Earth's surface temperature is the cycling of CO2 between the surface of the Earth and the mantle, right underneath. And without plate tectonics and the recycling of crust into the surface and back down to the mantle, it's very possible the Earth's surface temperature will not be nearly as steady through time, which is probably very bad for life. So that's just one example. Some other examples are, we are made out of certain elements like phosphorus and nitrogen, among other elements, of course. And these are elements required for life, right? And if we don't have phosphorus, actually there will be no life as we know it. And it turns out the cycling of crust into the mantle and back out again through plate tectonics also regulates the amount of phosphorus available to the Earth's surface system. So in these ways, this slow motion of continents and plates and their interactions with each other actually make the Earth what it is, and there will be no life as we know it on Earth without plate tectonics. There might be some sort of life, we don't know that, but certainly not the way we have it today. So understanding when plate tectonics started on Earth and what form it might have taken, right? Was it very similar to today in terms of speeds and how many plates we had and things like that? Or is it very different? That's very important for understanding when did our Earth become habitable? What are the conditions on Earth that allowed life to flourish? And so that's probably the main end goal of my research, right? To understand if you were to stand on the Earth 4 billion years ago, what would it be like? Would it be like the present day in many ways, or would it be oceans and mountain ranges and a relatively stable temperature? Or would it be something like Mars and Venus without plate tectonics, right? Which is crazy high, crazy low temperatures and no water cycle to speak of. So I think that the main insight from my research is that even 3.5 billion years ago, the Earth actually had plate tectonics operating in a pretty similar way to today. Maybe there's some differences, but by and large, a lot of the same systems of the Earth that has made life possible and made the environment stable for life were already in existence very early on.
Okay, cool. And then do you have any ongoing paleomagnetism or paleoclimate research at the moment? And kind of, if you can tell us a little bit about what you're looking to learn more about with those projects.
Yeah, as usual in an academic lab, I think we have a lot of topics going on at the same time, and everything I've talked about so far, we have some project in each of these topics still ongoing. We were lucky enough recently to be approved to have a sample of the asteroid Bennu, right, which is the asteroid that NASA sent a spacecraft to visit a few years ago, and the samples came down, I guess about a year and a half ago at this point. It's not much material. We got, oh my gosh, about 1/10 of a gram.
Oh,
But that's
wow.
enough. That's enough for our work. And we've been doing the magnetic measurements in my lab to understand the environment in which these very early dust particles and asteroids formed in the solar system. So this is a really rare opportunity, right? Because it's a rock that came directly from space. It didn't go through the Earth's atmosphere, right, which actually destroys a lot of rocks as they fall. Only a very small amount of rock comes down as meteorites. So we get sort of this unbiased sample of what is actually up there and try to understand the magnetic fields and the formation environment of a class of rocks that we otherwise would not easily find here on Earth as meteorites. We're continuing our work on understanding early Earth conditions. All right, so if all goes well, we're trying to go to Australia again this summer. Well, I was gonna say something that you'll probably cut out, but I'll say it anyway, just in
Sure.
case you don't want to cut it out. I mean, the recent funding freezes from the federal government has affected our plans to some extent. We had a grant from the National Science Foundation that was supposed to extend our work to understand early Earth tectonics and environment habitability by going to Australia and doing field work. So it looks like that's probably not coming through. Certainly not anytime soon, maybe not ever. So our plans are a little bit in flux now, unfortunately, but otherwise we would be planning to go back to Australia.
Hmm.
And this time trying to understand first in more detail, like what was driving the motion of plates back in that time, right? We found so far that plates were moving around just like today, but just because they're moving around doesn't mean they necessarily had the same implications for how much volcanism there was, how much land there was, how much ocean area there was. Anyway, there are a lot of questions still open about exactly what plate tectonics was like and how that really affected surface environments on the early Earth. Another area we might try to go into is understanding the history of the Earth magnetic field
Hmm.
by sampling some rocks that record the strength of the Earth core magnetic field as far back as 3.5 billion years ago. So yeah, we're hoping to try to sort of run these projects with what resources we can right now.
Yeah, no, I'd love to leave that in. Personally, I think highlighting everything good that the funding can do is important.
Yeah, I did see you had a recent one about science funding, right? And I appreciate doing that.
Yeah, of course. I live in Cambridge as well. So it's obviously going to be an impact on the local community with any amount of funding that goes in either direction. But more importantly, in the long term, I think it's a personal view that the more science research is better. Yeah, and I think a lot of people would also feel that way if they were exposed to more research and exposed to more of the results that we get out of this research. I think people would be interested in it and happy to happy to approve funding for it. Yeah, this is my personal soapbox, I guess.
Yeah. Yeah, I remember when I was a graduate student, maybe 10 years ago, there was a poll I read. It's kind of a clever poll, I thought. It's basically asking people how much they thought the government spent on different things. And then of course the article also provided what the government also actually spent on different things. And NASA was a real standout in how much people overestimate the amount of their budget, right? So people thought they got close to 10%, if I recall correctly, of the federal budget. In reality, it's again about half a percent, right? So about a 10-time increase in the perceived amount of money they get versus how much they actually get, which I think is a really big win, right, for NASA, right? If you can spend $1 on anything, right, and have people think you spent $10 on it, that means you're probably doing a pretty good job. You're being very efficient with those dollars. So NASA, I mean, I think it's one of the most salient and prestigious parts, right? And it just gets tremendous street creds, right? No matter what you're interested in. I've worked with a lot of different students and postdocs over the years here. I had a postdoc from Germany, for example, and he graduated from one of the best universities in Germany. He's had no shortage of being exposed to very high level research. But when he came to my lab, he bought a NASA shirt and he wore it around, right? And I asked him, like, yeah, what's with the NASA shirt? And he said, like my salary is being paid by NASA because I'm working on a grant that NASA gave to my lab. And I'm just really proud to be working for NASA after all these years. And, just hearing that, like someone, again, who has been exposed to the best universities in Europe, right? And coming here and thinking just working for NASA is a privilege, right? I think just tells you how much street cred and respect NASA gets and the science they do gets. And I think it's easy to overlook, right? Because you can't necessarily measure, right, how many pounds of respect NASA gets, but just anecdotally and in terms of perception, I think science is earning us a lot of respect, right, as a country, as a society.
Yeah. Yeah, absolutely. And I guess in that category, how have you seen educating students and educating the public? How has that changed for you over the years? Have you noticed any differences happening?
Well, I guess I've been a professor here 8 years, which I guess in a great scheme of things isn't that long. I think it's been pretty steady. I think the students we've had, well, I think after COVID, right, that right around there was definitely a dip in sort of student engagement and just general enthusiasm about school, I think. And I'm sure that goes for every college and high school and maybe even elementary schools that you can think of. But overall, I think the engagement now compared to before the pandemic is pretty similar. I've had the privilege of working with local teachers, middle school, high school teachers mainly, on some outreach programs. We did this in a self-funded program to supply about 20 local teachers with telescopes and had a 2-day workshop on how to use them and how to prepare some lessons for their classes. So they are, yeah, it's just really refreshing to work with teachers, right? Because you realize that they and their students really are curious, right, about the latest science and really want to learn. It makes me feel more gratified to do what I'm doing.
That's great. That's great. And what would you say has been your favorite project over the last couple of years to learn about and share with other people about?
Well, I think probably the one that stoked most sort of interest and imagination is about plate tectonics, which, if you call it just how fast are plates moving around, it's maybe seems a little abstract. But again, the fact that plates move around and they hit each other, they kind of glide over each other and push things into the mantle. That sort of recycling, right, between the surface environment and the deep earth is absolutely critical for establishing the surface for life, right? For making it habitable, for regulating temperature and having the elements available for life. So just inviting people to think about, right, how did life start on Earth? Why did it only start in a place like Earth, right, and not on other planets? Right? What is it special about Earth, right? Is it because of plate tectonics, or what part of it is because the Earth had these mobile plates and moving around long ago? I think that gets people excited, right? Just to think about if you were to stand here on Earth 3.5, 4 billion years ago, what would it have been like? And I think it goes at a deeper question, right? A deeper interest that I think everyone has to some extent. Like where did we come from? And is life something very unique and very rare in the universe, or is it something more common? And I think, there are a lot of areas of science that tackle some aspect of this question. And the part that I have in it with my early Earth geological work is trying to understand, how unique is the Earth environment such that life was able to exist? Right? Are these conditions that are easily found on other planets, or is there something very special about Earth? And I think that always gets people excited, right? To just think about life in the universe and how it came to be.
Yeah. Yeah, absolutely. And then the last question I have for you, I guess. Yeah, what's been your favorite class to teach to everyone over the years? What's been your favorite thing to teach students about, and what do they get most excited about?
Ooh, that's a hard one. Yeah, if you permit me, I might have to mention two because they're very different classes, hard to
Yeah,
compare.
please.
One is my kind of bread and butter planetary science class. I talk about formation of the solar system in a lot of detail. Talk about what is special about different planets and different bodies in the solar system. So that's a more advanced class. It's more for like second, third fourth year undergraduates. Some graduate students take it, and that's cool. I think partly because everyone always gets excited about planets, right? It's just cool, right? Like you start thinking about, oh, like could there be life on Europa, right, on the moon of Jupiter? You know, these questions that are just kind of intrinsically exciting to people. And it's also a really good opportunity to talk about how science works, right? In the sense, the information in that class about how the solar system formed, where are the most likely habitable places in the solar system. These things have changed since even just a few years ago, and certainly since 10 years ago when I was a student. So yeah, I would say that that's that opportunity to say, okay, this is how science actually works. Here's some results that changed our understanding from just a couple years ago, or maybe earlier this year. I think is very valuable for the students. And quickly, I guess I just want to say I personally really enjoy another class, which is a seminar that I teach for first years. It's called What Do You See in a Night Sky? And it kind of builds off of my couple of years doing ethnography. And we talk about basically how different cultures around the world look at the sky, what they see in the stars, how to use the stars to tell time, and so on. And then we sort of migrate the topic towards the end of the course on like early scientific astronomy, so Babylonian, Greek astronomy, and how that became more scientific, quote unquote, through time. And we have this discussion on what constitutes science, right? If the Babylonian observer was writing down, oh, here is a shooting star that went in a certain direction, and then the next day some important person died. We kind of think of that as superstitious, of course, today, but if you think stars, if your worldview is that stars are some kind of divine messaging system, right? And you keep meticulous records and look for patterns in these things. To me, I think that's a form of sort of proto science, right? You look for patterns in reality and try to interpret them. Um, you know, in the end, I think they were kind of barking up the wrong tree a little bit, right? I don't
Mm.
think comets really predict when the next king is going to die or something, but I think they're kind of on the right track, right? That reality has patterns that we can understand, and I think that kind of manifested more and more during the first millennium BC when you had the beginning of Greek astronomy towards the end. So yeah, I think that class is really interesting as well, just to sort of teach the meaning of science and how we derive knowledge through this backdrop of astronomy.
Fantastic. Thank you so much, Professor Roger Fu. Really, really appreciate your time today.
Yeah, no, thank you. This is fun.